we spend so much time to study series. Actually, the motivation to study series is to study power series, okay? And we're trying to understand a very large class of functions which can be represented by power series. And because the reason is, see, when you're trying to solve a differential equations, you know the solution exists. In mathematics, we can prove that. But you cannot, you cannot express it as a elementary functions. They only limited elementary functions which are well understood, and we use it. Okay, combination of these functions. Okay, and there are more than infinite many other functions which cannot be expressed by using elementary functions. Okay, so I just said that there's just too many functions. Then you will say, well, we can introduce more elementary functions, spend more time and then name them and understand that, but that's still not enough. After a couple hundred years, we decide just only like trigonometric functions, polynomials, and this can be, studied, and we can use that. We are very familiar with this type of functions, okay? But that just as I said, too many functions. But fortunately, almost all the functions can be expressed as a power series. That's a good part, okay? And we learn that, at least, we learn that, right? And when our one says this is a function, it's elementary function, it's simple. We know that this is the first function we learned that, okay? Can be expressed as power series, okay? When x is less than 1, up to x. So it's not too bad, right? Just 1 plus x squared plus x cubed. So you can see all the coefficients. Although this series is defined to be, it's a limit, infinite many terms there. But you can see through, understand all the coefficients. Okay. So this is our, the function we studied before. Okay. This is our starting point. Then we can define, then we see that every convergent power series define a function, right? From last class, we see that, okay? So we can consider a power series, okay? We assume that this is a convergent, and we are given, assume that, yeah, this is a x minus s less than r, where r is a radius of convergence. Okay. Then we get a function, right? Using power series, we get a function. Okay, this function is defined on the interval. Okay. So every power series, okay, defines a function on the interval of its convergence. Okay. Later, I'm just trying to show you almost all the functions can be expressed as power series, okay, around some point. Okay, so we get a function, and what is good about this function? we find out this function, yeah, f has the following property. Right. F of x is differentiable. And as many times as possible, as you wish. Okay. On the interval, on this interval, a minus r, a plus r. We don't need to worry about the endpoints. Not only that, and that's the first thing. Second, the power series. This power series, when you differentiate, right? You can differentiate many times. Let's differentiate one time. Okay. This one, okay, has a radius convergence equal to r. Okay, so this one for this series is convergent. The radius is convergent. The radius of convergence, sorry, is going to be is still r. Okay, so it's not going to be convergent on over a large interval or small interval. It's still converging on the same interval. Third point, the derivative, they're going to be the same. Okay, and that on the interval. So it's three parts here. Okay. Okay, and then you can differentiate it and again because this is you get a new series, right? And the new series, the radius convergence is r, and then no matter how many times you differentiate, so this, then you get second derivative, right? The function is differentiable again, and that is going to be, I think we're going to start from, you can start from 1 here, because when n equals 1, n equals 0, that's going to be 0. So now you can 2, Cn, n minus 1, x minus a to the n minus 2, okay? And this holds over that interval again, okay? So actually implies three things. One is the derivative function is still differentiable. Second, the series on the right-hand side still have the same radius convergence, r. And third, they're equal over the interval, okay? And then you can differentiate this again, right? Then you differentiate this again. And now here we assume that a is positive, okay? Or I is positive, okay? Otherwise, it doesn't make any sense here, this interval, right? So we, at the very beginning, we assume that, we assume that I is positive or infinity, okay? All right. Then the third derivative, it can be Cn n minus 1, n minus 2, x minus a to the n minus 3, okay? And the power series on the right-hand side still has the same radius of convergence, r, okay? And then equal to the third derivative of the function. So you can, now, some kids like trying to figure out the pattern, okay? So you can figure out the pattern. And the case derivative of the function, okay? So that's going to be n equals k and Cn n times n minus 1, n minus 2. Here's n minus, I think k minus 1, okay? So x minus a to the n minus k. And that holds on the same interval. So that means no matter how complicated of the coefficients, for the series on the right-hand side, the radius convergence is still r, and then it's convergent to the case derivative of the function, okay? Right? And the leading term, let's take a look at the leading term, okay? Let's look at the leading term. when n equals k, so Cn, and then actually is k, it's a ck, okay, when n equals k, and k minus 1, blah, blah, blah. The last term is 1. That's the first term, okay? And the second term, ck plus 1, k plus 1, and k, and so on, and that's going to be actually 2, I think. Yeah, okay? And that is x minus 1, minus a to the power 1, okay? And then keep it going. So you have the most general term is in the middle, right? Okay, x minus a to the power k, and the plus higher one. Okay, so this is a series. So this is a leading term. Now, as you can see that, if I plug a for x, I get the value of the case order derivative at a. And then all the term is gone, only the leading term, k times k factorial is given. Okay. So we get the following identity. Wow. So what does that tell me? That tells me we get the following theorem. Okay. If a function, okay, f of x has a power representation, okay, at a with radius of convergence r, right, greater than 0, then i.e. f of x equals Cn x minus a to the nth power, okay, is part. Then this coefficient, okay, is uniquely determined by the nth order derivatives of the function evaluated at the point A. Okay, so that means power series is not only just unique, right? If the function has a power series representation, you can have another power series. Not only that, and the coefficient is related to function by this simple formula. Okay, so if I ask you to find the power series representation, and all I have to do is just find if you want to find the power series representation, and all I have to do is just find the coefficient, right? Now, what is logical here? That means if you find the partial derivatives, if you find all the derivatives and evaluate at A, and you define Cn, and you get power series, okay, for a given function f, does not mean the series is convergent to the function, okay? So this is a logic. Yeah, we should be very careful, okay? So here's a remark, okay? Given a function, okay? Given function f of x on the interval a minus little I and plus r, okay? Here is positive, some interval, okay? If the function is differentiable many times as you want, then you let Cn to be this, okay? Then you consider the corresponding power series, Okay, now the question is, what is the radius convergent? But that the radius convergent maybe it's different from R. Okay, I just care for some small r, so I'm going to use a delta instead of R. Okay, so make it easy. Okay, for some delta on interval. So the function, we assume that function differentiable, so you can get the number. But then you consider this series. Okay, the radius of convergence can be less than delta, can be greater than delta. Okay, that's the first thing I want to say. Second, the series might be convergent, but I cannot tell whether it's convergent to the same function, right? Because the above statement does not tell you that. So let R be the radius convergence. Okay, we even assume that R is positive. Okay, yeah, we can assume R is the radius of a convergence. So every series you can have a radius convergence, right? So that means the functions, yeah. But question is this equal to? Okay, equal for x close to a. I'm not sure on how big of the interval. The right hand side, the left hand side of the function is only defined on the interval from, right? Plus minus delta, a plus minus delta. Okay, but if you just look at the series on the right hand side, it's convergent over some interval. The radius of convergence is up. All right, but we want to make sure they're equal. So it's not clear. No such theorem guarantee. Okay, but I do get a power series associated with that. Now, what I can tell is if fx indeed equal to some power series, then that power series, the coefficients must be given by this formula. That's what it says above them. If, okay, so that's assumption. It's a very strong assumption. If you know ahead of time, f of x has a power series representation, then the coefficients must be computed using the derivative of the function. Okay, evaluate at the point A. But given the arbitrary function, if you don't know whether this has a power series representation, then you still can differentiate, right? You assume the function differential many times. And then you make a power series. You know that if the function has a power series representation, then that must be the one. Right, if, okay? So now you get power series, no, right? Then we don't know. You cannot, until you prove it, you cannot say this equal to f of x. And this power series is equal to f. Maybe they're not equal. Right? It's not necessary. See, this is logic, okay? Be careful about the logic. Which one first? All right, so let's take a look at the function. Given the function f of x, okay, 1 minus x to the negative 1, which is just 1 of x, okay? Now this function, we assume that this function is defined on this interval, okay, right? So we pretended we have never learned any powers we know. We haven't studied, we pretended we don't know f of x can be, has a power series representation, okay? So we're trying to find it, okay? Right? What do we know about the above theorem is if f of x equals some power series, right? Okay, and x is less than some delta, right? Small number. Then this Cn must be, right? Okay, let's find out what is Cn. Right? You can determine the coefficient, right? So it's not if the function is positive circuit, and must Cn must be computed by this. Okay, let's do the computation. Okay, f prime x when the differentiate is above 1, right? Because f of x is going to be 1 minus x to the negative 1, so it's negative 1, 1 minus x to the negative 2, and times the derivative of 1 minus x, which is negative. So negative becomes positive. Well, let's continue. F double prime, we get negative 2, 1 minus x here, negative 3, and times negative 1. So negative 2 times negative 1, it's just 2. Okay, we have to figure out the pattern. Okay, now there are some students who was trying to use this idea to determine the coefficient, but they never figured out the pattern. Okay, you have to differentiate 3 times, so you get 2 is still there, negative 3, 1 minus x here, negative 4, and negative 1, right? Negative 3 times negative 1, you always get a negative sign. So that's why the negative sign never shows up. Okay. And I think I'm going to figure out the pattern. If one more times, yeah, we probably can do that, right? Right, negative 4 times negative 1 is going to be 4. So 2 times 3 times 4, 1 minus x to the negative 5th. I think I have a pretty good idea. So the nth power, the nth order derivative is here is going to be 2 times 3 all the way to n. Here's 1 minus x, negative n plus 1. Okay, this is the general formula. Okay, so what we have here is the front side is n factorial, 1 minus x to the negative n plus 1. Okay. So now, Cn is going to be the value function at 0 and divided by n factorial. The value function at the end is going to be n factorial 1 minus 0 to the, right? Here's n factorial, and clearly it's going to be 1. Okay. So we get this series. But Cn is always equal 1. Okay, so we get this series. And you can even tell the rate of convergence, okay, is also equal to R, okay, for this series. My question is it equal to the function? Okay, question. We begin with a function. Now you get a series, and you have to go back, right? Is this function, yeah, right? And of course, you say, oh, that's obvious. We knew that before, right? Yeah. So answer is yes, but you prove this identity using different method, right? All right. So the answer is yes. Okay. The answer is yes by the geometric series test. Okay. The geometric series test tells you this series is converging to 1 over 1 minus x. So we're lucky here, we indeed, and then not, yeah, we can show that it's convergent. But in general, if you begin with a function differentiable many times, then you can determine all the coefficients. Then you get a power series. But does that mean that power series number 1 is convergent or convergent to the function? We don't know. So let's give a definition. Okay, given a function f of x, okay, differentiable many times at number A. Then you get then we get a series, right? The series, the coefficients are this, right? But we don't know whether this is what is the radius convergence, whether it's equal to the function. We don't know. But anyway, this series is called, we give the name here, called the Taylor series of F at A. Okay. Why it's called Taylor series? Because Taylor was the first person series to study this problem. Okay. So given function, I want, the whole point is I want to, given function, the motivation here is trying to find the power series representation for that particular function. Right? So you find the only unique candidate, maybe that candidate disqualified. Okay, Taylor's work is trying to tell you when he checked, when this this candidate is indeed the power series representation. Okay. Okay. So our motivation is find given a function differentiable on some interval nearby A, including A, and we want to know whether this is this has a power series representation. So you want to prove if it has power series representation, we have to prove that, yeah. So such power series representation is unique and convergent. Right? You have to prove that it's convergent to the function. Okay. To prove, and the partial sum, yeah, this partial sum, yeah, we let this to be the partial sum. Okay. And the difference is going to be the function minus Tnx. So we don't know the gap between the function and this polynomial of degree n is getting smaller and smaller. We don't know. So given a function, you get so-called Taylor series, which is a unique candidate for the power series representation of the function. Then if you find the radius convergence of this power series, right, the next question is whether this is a convergent to the given function. Right? How to check? Let's take a look at the example first before I do it. Okay, so let f of x to be 1 minus x, right? Then you get the Taylor series. Okay, this is a Taylor series. So Tnx is going to be n k start from 0, right? So actually, this is just k star from 0 and xk. It's 1 plus x squared all the way to n. So remainder, the difference, right? So fx minus tnx. Let's look at, right? We can study this in this side different way. Okay. All right, so this is going to be we can combine this two, right? So it's going to be 1 minus x to the n plus 1 divided by 1 minus x. Yeah, this is going to be 1 minus x to the n plus 1 and 1 minus x. So it has a common denominator, so it's n plus 1 and 1 minus x. And I think the gap is getting small, so for any x, yeah, for x less than equal 1, the limit of this is going to be 0, right? So the difference f of x minus, and that is going to be absolute of x n plus 1, 1 minus x. Okay. Actually, this is going to be approach 0 as n approaches infinity for x less than 1. Okay. You can tell exactly what is the error between those two. Yeah. All right. So what it did by Taylor? Taylor's work. Okay. Taylor find out Taylor actually get an estimate. Taylor says if okay, the nth order of the function, the n plus 1 of function is less than or equal to some function, some number depends on d. Okay, for x minus a less than or equal to d. Okay. Then he says a different, which is going to be the f of x minus tn, right? Can be estimate okay. So x minus a is even you can mention that this is n plus 1 factorial, and this is just a d to the n plus 1 because x minus a is equal. Okay, so the right hand side now, and with yeah, if we can show this converging to 0, then so if the limit okay, m and d n plus 1, this is 0, then f of x is going to be the limit of right. Okay, for x minus a not less, yeah, for x minus a less than equal to d. Okay, so these definitely smaller than the radius of convergence. Okay, these are smaller than or equal to the radius of convergence of the series, right? This implies these smaller than or equal to radius of convergence. The radius okay, of the series on the right hand side. Okay, we just show this is equal, and for x minus a absolute value less than or equal to d. So that means two things. One is the power series on the right hand side is convergent for x minus a less than or equal to d. So the radius of convergence should be greater than or equal to d. Okay, so it's not only convergent, it's also convergent to the function. Okay, clear, right? That is a good theorem done by Taylor. So Taylor was trying to see, give me a function. I can compute the derivative for many times, right? Then I construct the unique candidate for the power representation of the function. But still, we don't know how, right? We can also figure out the radius convergence for this new power series, but we don't know whether this is convergent to the given function or not. Okay, Taylor gives you idea how to check that. Okay, I think if you always keep in mind that doing like that, when you take a course, right before you study the next section, you're trying to figure out how can I check whether the series I create is convergent to the original function. And if you're able to find the theorem and figure out how to prove that, then this is your theorem, okay? So you have the potential to be a mathematician. All right, okay. In calculus, of course, there's not much you can find out. Because it's so many people, studies calculus, and almost all the formulas has been discovered. Okay. So this is good. Okay, so let's take a look at the following function. I'm very curious about this exponential function. Okay, I want to find out the power series representation, if any. Power series representation of for the function f at a equals 0 if any, right? Okay, let's say that. All right, so what I'm going to do, first of all, find the candidate, right? Find the candidate. Second, I have to prove that power series convergent to e to the x. You have to use a Taylor side here. Okay. I think Taylor was a British mathematician. Yeah, that was many years ago. 100 years, 200 years ago, right after Newton. Yeah, during that time, United States here. Well, no United States, Americans, the Native Americans here. Okay. No calculus. The whole the whole country that time, nobody knew that. Right? Nobody came to this, right? To this land at that time. Okay, so that is the case. So let's figure it out. Okay, first of all, let's find a candidate for this series, power series candidate, right? The unique candidate, okay? The unique candidate is the Taylor series, okay? Now it's also called the Maclaurin series when a equals 0. Yeah, same time Maclaurin, did some work in the literature, okay? So we need, so this is a series. N, right? Cn is going to be the derivative of the function divided by n factorial. Let's find out. Okay, so I'm going to find out the derivative. Wow, e to the x is a unique function which can be differentiable many times as you want. You get always the same result. That's easy to figure out the pattern. Okay, so nth order derivative is going to be the same function. Great, so Cn is going to be f of n, 0 n factorial, which is e to the 0 n factorial, which is 1 over n. Okay, that's a Cn. So we get the Taylor series. Okay, of the function. But I don't know this is going to be 0 or not, equal to the function now, right? I did get n factorial here, n start from 0 and x to the nth power. Number one, what is the radius convergence? Number two, is it convergent to the function on the interval convergence? Right? You have to answer these two questions. Otherwise, if this series is divergent, then you say the function e to the x has no power series representation, right? If you cannot prove, if this series has a positive radius convergence, then it's convergent on some interval, right, around 0. If we cannot prove it is convergent to e to the x, then you cannot claim this is a power series representation. Okay, so you have to prove it. All right, let's think about it. Okay, we have time, so I'm going to So how can I prove that? Now we have to use a Taylor's idea, right? I want to prove that it is convergent. I want to show that, right, this series, okay, is convergent to e to the x, okay, for any x. Okay, of course, this also implies the radius convergence is going to be, the radius convergence of the power series is going to be infinity, okay? How can I do that? Well, go back to look at Taylor's theorem, okay? Let's go back to Taylor's theorem. Okay. Taylor says that, okay, if you estimate the nth order derivative, okay, and you get an upper bound over some intervals for some d, and then the error between the function and the partial sum of the power series is going to be estimated by this. If that one converging to 0, then I'm done, right? So okay, fine. So what is d? How can I choose a d? Well, d take arbitrary d, right? Just assume that, okay? Yeah, I just let the d to be positive. That's it, okay? Then I'm going to look at this function. This is a e to the x again, okay? So fn plus 1 x is going to e to the x. This is less than equal to e to the absolute x, less than equal to e to the d, if x is less than equal to d. Do you agree? If I agree, let's move on. Okay, great. Okay, so then we have f of x minus partial sum. It's going to be, right, e to the d, I think. Here's n plus 1 factorial and x to the n plus 1 if x is less than equal to d. Yeah, right? That's what we got here. Yes, so, okay. So this is what we have here, right? Okay. So now I don't need to put x there. I can depress x by d. So everything depends on d. Okay. My question is whether this is going to be, this holds for x less than equal to d, right? So So I claim this is a constant, don't worry about it. This one is always equal to 0, okay? I can approach 0 when n approaches infinity, okay? That's a different story. Okay, so that means for x, absolute x less than or equal to d, this is always convergent. Okay, that implies this is x to the n factorial, which is a limit as n, right? This is always equal to f of x, which is e to the x for x less than or equal to d. Now, since d is arbitrary, so that's what we always, okay? This is for some d, right? For any d we choose, okay? This implies for any x, since d is arbitrary, okay? All right, so we get identity. E to the x can be expressed using this formula. Wow, so now using calculus, we can easily get an estimate for the e. So e is going to be e to the 1. So, right, that's correct, right? So how do you estimate this? Well, you just choose a sufficient large partial sum, right? So you can get the good estimate. So E is estimate here, for any capital N. Okay, this is going to be 1 plus 2 factorial. No, actually 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial all the way to n factorial. And nowadays computers can do very fast computation. So you can let capital N to be 1 billion, 1 trillion, then the number, the sum on the right-hand side is almost equal to the number E. This is a mystery number, okay? Number E was introduced as a limit of some sequence, right, by mathematicians. And this is problems from a finance business, okay, investment. Okay, so E has another formula, 1 plus 1 over n. This is a formula coming from the investment, okay? If it's compounded continuously, you divide the whole year into n times, n can be 4 if the interest is compounded quarterly, n equals 12 if it is compounded monthly, n equals 360 if it's compounded daily, usually compound. Okay? If n equals 3,600, it's compounded every second. Okay, so when n is getting large and large, and you get a number E. Okay. So there are many formulas about the E. This is only 2 formulas. And in either case, E is defined as a limit. Okay? Last time we were talking about the movie about Ramanujan, right? The Indian mathematician, he's a genius guy. So he knew he knew infinity. Okay, so he got so many series represent something. Yeah, and he wrote down without any proof even, and many mathematicians don't know how did he get it. Somebody says maybe he could talk to the God, because those are there, okay? We just discovered, okay? Right? We did not create things. Scientists do not create things. Scientists just discover things. Okay? Engineering, what's the difference between engineers and scientists? Engineers don't have to understand science, but they can make things, put together lots of stuff. Okay, you can say they created things, but in some sense, just put together a puzzle, because this is they have to follow certain rules, right? So yeah, there's some difference in science in engineer. You have to learn science. Yeah. Okay, so you can make new stuff, but you don't create some new things. You can make a new airplane. Okay, rockets. Okay, that in yeah, that's what I want to say. Yes. Right. So here we just discover, we don't create. Of course, we introduce a notation, E thing, right? But then we don't create. This is an identity. It's there. Okay. All right. So using this, I can yeah. So recall, right? So e to the x, let's say, is always equal to x to the n factorial, right? So how about e to the negative x? No restriction on x. I change the sign, right? N and the x to the n's power. Great, right? Then e to the x plus e to the negative x divided by 2. This is hyperbolic cosine x. And you can add those together, okay? There is a general formula. If you have two series convergent, then you can add them together. You get two new series, okay? Just add the corresponding coefficients together. So it's going to be 1 over n factorial plus negative 1 to the n factorial, then x to the n, right? Then clearly when n equals r, they're all gone. Only when n equals even, n equals 2n, then you get, okay, m equals 0, 2n factorial, x to the 2n. That's it. Yeah. Okay, just 1 over 2n factorial plus 1 over plus 1 over 2. So it's 2 divided by 2 squared. Okay, so this is an even function, clearly, right? And then e to the x minus e to the negative x divided by 2 minus negative 1 to the n factorial. Now this term is not going, the coefficient is not going to be 0 only when n equals 2m plus 1, right? So m starts from 0. Okay, so you get negative, it should be 2, right? It's odd enough. So that is going to be when m equals 0, 2m plus 1 factorial x to the 2m plus 1. Okay, so this is a hyperbolic sine x. Now, when you differentiate hyperbolic sine x, you can get the cosine x, hyperbolic cosine x. Yeah, that's easy to see that, right? Let's look at the derivative, right? You can differentiate every term inside a power series, so 2m plus 1 and x to the 2m, right? And after you simplify, the coefficient is just the 1 over 2m factorial. And this is nothing but hyperbolic cosine x, you see? So we get a derivative for hyperbolic sine x using power series. All right. Now, if I ask you to find the power series representation for hyperbolic sine x, how do you do that? Do you need to go through the original definition, find the Taylor series, then prove the convergence? Prove the convergence, you don't need to do that. You just use the already known result, e to the x, right? You already know the result, so you don't. All right, so we got power series for sine, for hyperbolic sine, hyperbolic cosine. Then it's natural question. What are the power series representation for cosine x and sine x, right? The elementary functions, right? Polynomial, you know, right? 1/1 minus x, right? And natural log of x. We got all those power series representation, right? So we are curious about sine and cosine. I want to find the power series representation, okay, for f of x equals cosine x and f of x equals sine x. Okay, I'm going to just do the I'm just do the sine x. Yeah, just to look at sine x. So similarly can do the cosine. Okay, just for this function. Right, so I don't have any known results I can use, right? So at the very beginning, you have to do some hard work. Then you can use that to find the power series representation for cosine 2x or for cosine square x, for example. Okay. Right? And they're using this. So how can I do that? Well, the candidate, right? There's only one candidate. No other choice. Either you approve it or you give up. Right? And here, you know, in the United States, we have two candidates for president. Right? You can choose one or even sometimes you don't like any of them, or sometimes you like both of them. But some other countries, there's only one candidate, no choice. Like in Iran, for example, right? Or North Korea or China. Okay, so we have only one candidate here for the power system, bad or good, okay? We have no choice, but only we can prove it's bad, then we don't have power system representation for the sine x. And if it's good, we use that. Yeah. Sometimes it's not always bad. Sometimes maybe reasonably good, it's possible. Okay. All right, so let's take a look at this. So let's see that only candidate is this one. Right, and it's at the origin, so I'm going to look at this. So I have to do is find the derivatives. Okay, so f x is sine x, then f prime x is going to be cosine x. Now we have to figure out the pattern, okay, in order to find the higher order derivatives. In the class, I spent so much time to find the power series representation, but does not mean you have to repeatedly doing this. I saw, you know, I saw something repeatedly do the same thing. If I ask you to find power series representation, okay, you know, if I ask you to find the Taylor series representation and Taylor series for the function, then you just find this derivatives, okay, and you don't need to prove it's convergent to the function. But if I ask you to find the power series representation, not only just find the Taylor series, because this is only unique candidate, you have to, yeah, the candidate is going to be the Taylor series. But you have to prove it's convergent to the function, okay? So second derivative is negative sine x. So now you get negative, right? The third derivative, I get negative cosine x. And keep it going. The fourth derivative is going to be sine x. So we come back to this. This is a sine, cosine, negative cosine, then sine again. Okay, so repeatedly, right? Let's write another one. All right, so what kind of, yeah, can we figure out the pattern? Okay. If you look at the even term, okay, you will see you always get sine x, but there's the coefficients in front of that. So that is going to be 2mx, right? It's going to be sine x always, but then there's a negative sign shows up. I think this should be m's power, okay? Now, if you want to look at 2m plus 1x, right? You always get cosine x. The question is, what is the coefficient in front of that? I think this is going to be, m is going to be, when m equals 0, I have a f1, that's 1. When m equals 1, it's negative, okay? Yeah, so this is also m, okay? So you can figure out the general form. All right, so now you will get 2m 0, that's always 0, and the 2m plus 1, 0 is negative 1 to the m's power. All right, so we get all the coefficients. So the candidate, right, Cn x minus, right, not Cn. Okay, first of all, you only consider other terms when m equals 0, f2m plus 1, 2m plus 1 factorial x to the 2m plus 1, right? And then the numerator will be negative 1 to the m's power, 2m plus 1. Okay, that's it. And you can also show that the radius convergence is going to be infinity of this series. Okay, I is going to be infinity. The question is whether this series is going to be convergent to sine x. So sine x could be expressed as power series, right? Cannot be expressed as polynomial. Okay. Right, so how do you do that now? We go back, right? We have to show that, okay, we have to prove this now. We have to estimate in order to remember the difference, right? Right, given functions, the Taylor series, right? You get the Taylor series. Right, and then you have this difference, right? The error, and this is going to be estimated by the n's plus 1's order derivative, right? Right, the error is going to be less than or equal to mn d n plus 1 factorial and x minus, in this case, is n plus 1. Okay, this x is less than or equal to d. Okay, these are an arbitrary. So I want to make sure this convergent to 0. Okay. Yeah, you let this, and if f n plus 1 x this can be bounded, okay, then you have this identity. All right, so let's take a look at the derivative, okay? So there's only two cases here. So fn plus 1, okay? This one, they're either plus or minus sine x, right? Or plus or minus cosine x. So in either case, I don't even know the details, but in either case, this is going to be less than or equal to 1. Great. Okay. So the error, okay, is going to be less than or equal to 1, n plus 1 factorial, and x to the n plus 1. Okay, this is going to be less than d to the n plus 1, n plus 1 factorial. All right, so clearly this approaches 0 as n approaches infinity. Okay, so that means the limit n approaching infinity, this one is going to be 0 for x less than or equal to d, but these are arbitrary, right? Okay, so that means you always have it's going to be sine x, right? For x less than d, but these are arbitrary numbers. So x is holds for any x. So we do get a little bit ugly, but we do get the power series representation for sine x. Okay, this actually hold because these are arbitrary. This is an arbitrary. If this is arbitrary, it doesn't matter, right? So then we get the identity sine x equals and this always holds for any x. Okay. This always holds for any x. Okay. And similarly, you can get the series for cosine x. But in order to get a cosine, I just differentiate to make it easier, right? I don't need to waste time to, you see that? Well, I don't need to waste time to find the candidate for the power series representation of cosine x. Then you prove the convergence. I already get a sine. So when I differentiate, right, I have, when I differentiate, this is a, right, and here's 2m factorial and x to the 2m. This holds for any x, for any x. Yeah, you differentiate every term. Then you cancel 2m plus 1. Now here's a question. Here's a question. Find the power series representation for sine square x, right, at a equals 0. Okay, now when you look at this, okay, then I have to find the derivatives, and you find out it's too complicated, the derivative, it's difficult to find the pattern. Okay, don't repeat what I did for sine x. What you should do is you look at this is going to be, okay, it is going to be 1 minus cosine 2x divided by 2, I'm pretty sure. Yes. Okay, so it's going to be 1/2 minus 1/2 cosine 2x. All I have to do is apply this formula to here. Okay, so it's going to be 1/2 minus 1/2 m equals 0, right? So here's 2n factorial negative 1 to the nth power, and x becomes 2x. right? X become 2x. That's it. So you're done. Right? Now actually the first term is going to be 0. When m equals 0, you will get 1/2, 1/2, so they're all gone. So actually you should start from m equals 1. Okay. So it's 2 to the m and x to the 2m. Okay. And you want to put all the numbers inside, and you get 2m factorial, and -1 here's m plus 1 because I have another negative sign, and here's 2m minus 1, x to the 2m. That's it. So this is a coefficient. You see, so quick, right? You just use a no result, okay, and to modify it, and then you get the power series representation for the function, like sine squared. If you try to find the partial derivatives, get a Taylor series, then you prove its convergence. Number one, it's so difficult to compute the high order derivatives. Number two, you still have to prove that it's convergent to the given function. It's not easy, okay? So don't do the stupid things, okay? And yeah, and you shouldn't, okay? Repeatedly use the same idea to find the power series representation for the function you are given. Okay? You should find the already known results and then try to modify it, and then you get the answer you want.